talk at this conference. I'm very happy to be with you today. Introduced, my name is Clement Gosselin. I'm from Laval University in Quebec City in Canada. And I'm assuming that most of you are not familiar with my university. So before I begin, I want to say a few words about our university. Laval University.
Excuse me.
Yes.
We can't see your screen.
Clement, can you share again, because we just stopped your screen.
Okay. Just a second. I will
Thank
go
you.
back here and share again. Okay. So you should be able to see my screen now.
Perfect.
Can you see my screen?
Yes, perfect. Thank you.
Okay, so I was saying that before I begin, I want to say a few words about our university. So Laval University is one of the top 6 universities in Canada for research funding, and it was founded in 1663. It's one of the oldest universities in North America. We have a population of close to 50,000 students. We're located in Quebec City. And more specifically, the Robotics Laboratory was founded in 1989, and we have since then published more than 600 papers. I'm holding the Canada Research Chair in Robotics and Mechatronics since 2001, and we are part of the Research Center on Robotics, Computer Vision, and Machine Intelligence, which includes about 13 professors and approximately 100 graduate students. So this is the ecosystem in which we are working. On the right-hand side, you can see on the top a picture of the city, and at the bottom a picture of the main campus of the university. So as a lab, for the Robotics Lab, our main contributions are in the areas of parallel robots, robotic hands and end effectors, cable-driven parallel robots, physical human-robot interaction, which we will discuss today more specifically, haptic devices, and assistive robotics. And the main contribution, or one of the main ways we contribute, is through prototyping. So we believe in building prototypes and testing ideas. And one of the reasons is because our leitmotif is that mechanics is at the core of robotics and should be an important component of the solution. So, like I said, our contributions include parallel robots. You see some of the robots that we've built over the years. And at the bottom right, you can see one of the kinematically redundant robots that we built recently. I will talk more specifically about this robot later. And top right, you can see a cable-driven parallel mechanism that we've built. We've also contributed to building robot hands and end effectors for space applications, for industrial applications, for prosthetics, and also for medical applications. So at the bottom left, you see the robotic hand, which is a commercial product that originated from our lab and which is not commercialized, now commercialized by Robotic. That company is a spin-off from our lab. We've also been working on what we call extrinsic dexterity, which aims at leveraging the contact with the environment to help grasping objects in more difficult situations, like, for example, here, picking up flat objects from a flat surface. So today I want to talk more specifically about how parallel robots can be used in the physical human-robot interaction. So first, I will give a very brief introduction on robots in unstructured environments, just to set the framework. Then discuss a little bit more about physical human-robot interaction, what are the requirements, and then I will present a series of applications. The first one is using the MacroMini approach for physical human-robot interaction, and then applications with robot link shells that we've developed, and then come back to parallel robots with kinematically redundant robots and how they can be used in pHRI. So just as an introduction for robots in unstructured environments, I like to make this comparison between the development of autonomous vehicles and the development of personal robots. So autonomous vehicles, the progress over the past decade or so has been very, very fast. And on the other hand, for personal robots, the progress has been slow. One of the reasons for this, maybe not the only reason, but one of the reasons is that for autonomous vehicles, the challenges are mainly the sensors and the intelligence, how to recognize the environment, to make decisions, and so on. But there is no challenge on the mechanical side because we know how to build cars. We've been building cars for more than a century, so that's not a challenge. However, on the right-hand side, for personal robots, we still have the same challenges in terms of sensors and intelligence. But on top of that, we also have challenges in terms of mechanics, because we don't really know how to build robots that are capable of performing useful tasks while being safe and lightweight and easy to use in a human environment. So there are some challenges there in terms of the mechanics, which slows down the process. So we're trying to focus on that aspect. So if we look at collaborative robots that we can find that are commercially available, you can see that these robots are based mainly on serial robot architectures, so that they have a large workspace. They use gearboxes with large ratios to limit the size and mass of the actuators, and they use force-torque sensors at the joints or at the end effector to infer the intentions of users. But the fact that such sensors are used limits the bandwidth of the interaction with the user. So in order to make these robots safe, what robot makers have done is they've reduced the speed and the acceleration for safety so that they can work together with humans. So in summary, if you look at these robots, they look very much like the standard classical robots that we had before. They're constructed in the same way. And that limits the way they can interact with humans. So what we believe is that if we rethink the way these robots are built, maybe we can achieve much better results in terms of the interaction. So one way to rethink the way these robots are built is to look at parallel robots. So in the past, parallel robots have had success in several applications. Like for example, here in industrial applications, in the flight simulator applications, haptic devices, and machine tools, and also precision robots. So parallel robots have had success in these areas because their fundamental concepts or their fundamental properties are well used in such applications. For example, the top right picture, flight simulator. You need to move a payload of 15,000 kilograms with 6 degrees of freedom. So clearly it's impossible to do that with a serial robot. So you have to use a parallel architecture in which, as you can see on the picture, the legs are loaded only in tension and compression. There's no bending in the legs, and this is why it works. Other applications, like for example, top left picture, the Delta robot. So for industrial applications, if we want to be moving very, very fast, then it's very nice to have all the actuators fixed so that the moving parts are very light, and so you can increase the accelerations by large amounts. So in other applications, parallel robots have failed because their intrinsic properties were not a good fit with the other applications. But for these specific applications, they've been very successful. So if we look now again at the physical human-robot interaction, the collaborative robot applications, what would be the ideal characteristics for such robots? First of all, they should have low moving inertia so that this would make them very safe. If there is a collision with a person, if there is little inertia, then it's much safer. Also, we think that these robots should be backdrivable. So if they are backdrivable, it means that a user can grab the robot and move it around without the need for a force-torque sensor. So using impedance control instead of admittance control. So if the robot has a very low impedance, mechanical impedance, that's possible. And finally, they should have a large workspace, including a rotational workspace, to sort of match the workspace of the human arm. Now, if we look at these properties and think in terms of parallel robots, So low moving inertia is definitely a strength of parallel robots because, you know, the actuators can be fixed and the moving parts can be very light. Now, can we make parallel robots bike-drivable? Yes, it's easier because since the actuators are fixed or close to the base, we can afford to have bigger actuators with smaller transmission ratios, which makes the robot bike-drivable. In terms of workspace now, parallel robots traditionally are not doing so well. So that's a drawback of parallel robots. And we will see a little bit later in this presentation how we can alleviate that by using kinematic redundancy. So let's first look at a first approach that we've tried to implement, which is the MacroMini approach. So this approach was proposed some years ago by other people, where in a setup you have a macro robot that is a larger mechanism with a larger workspace, but not necessarily a high bandwidth. And on top of this macro robot, we mount a mini robot, which is the interaction component with the user. So the user interacts with a more agile mini robot, which is then controlling the motion of the macro robot. So the role of the macro robot is to try to keep the mini robot within its range of motion, and so by moving it around. So to make this more concrete, we can look at the kind of motion that would be possible with such a MacroMini robot. Let's assume that the user is moving the mini robot with a sinusoidal trajectory, like a harmonic motion. So here on this graph, you have on the y-axis, you have the range of motion, and on the x-axis, you have the frequency. So I recall here that L is the range of motion of the mini robot. So if we assume that the mini robot has unlimited response, then if the range of motion of the harmonic motion is smaller than L, then the motion can be performed at any frequency. If the range of motion is larger than L, then it depends on the limitations of the velocity and acceleration of the macro robot. In other words, is the macro robot capable of following the motion of the input motion of the end effector? So the gray area on this graph here is the feasible trajectories, and they're limited by two curves. One is the velocity limitation of the macro robot. The other one is the acceleration limitation of the macro robot. So this is sort of the dynamics of these two robots together. So concretely here's an example of something we've implemented in the lab. You see the macro robot in this case is a gantry robot, a 3 degree of freedom gantry robot, and the mini robot is a small 3 degree of freedom translational parallel robot based on the Tripteron, a parallel robot that we've proposed in the past. So the user here interacts with the mini robot. The macro robot tries to follow that motion so that the user can interact with a very low impedance mini robot. So this is what you can see here on the video. I hope you can see the video well. So the person is interacting with the end effector of the mini robot, which is very dynamic. And it would not be possible to have such a response from the macro robot itself. But we can say that the mini robot acts more or less like a buffer between the capabilities of the user and the macro robot. So here's another video of the same system where you see the person performing a trajectory that requires quite a bit of agility and acceleration and swift motions. And so this is possible because the mini robot can follow the motion of the user, and the macro robot just follows the mini robot. Here in this case, the mini robot is passive. It could be active as long as it's equipped with proper sensors. So here's a comparison. On the left-hand side, you have the MacroMini. On the right-hand side, you have the macro robot with a force torque sensor. So I want to point out that on the left-hand side, there is a force torque sensor, but it's not used for control, just to capture the data of the interaction forces. So you can clearly see that it's much easier on the left-hand side to perform the task, which is the insertion of this peg in holes. It goes much faster, but most importantly, it's much easier. So the feeling is much better. The person doesn't feel like they're dragging the robot. It feels very easy, and the human can deploy their own impedance. So based on that, here are some experimental data that we acquired from this experiment. The graphs on the left-hand side are from the MacroMini, and on the right-hand side from the admittance control with the force sensor directly on the macro robot. And the interesting curves are the ones at the bottom. You can see there the force, the interactive force between the user and the robot. So on the left-hand side with the MacroMini system, the force is always below 1 Newton. Whereas on the right-hand side, it goes almost to 40 Newtons. So it really shows how the user feels that they're, dragging the robot and they cannot deploy their own impedance. So we ran a test to try to compare this with human capabilities. So we asked people to move the end effector along a certain rail back and forth between 2 points as fast as they could. So the red circles on this graph are the data from the experiment, and the purple dotted line is the interpolation that we did of that. So that represents the maximum human capabilities. And then based on the MacroMini system that we have, you can see the limitations in terms of velocity and acceleration. And you can see that at high frequency, we are able to match the human capabilities with our system. At lower frequencies, not exactly. We're not exactly at the human capabilities. But we have to keep in mind that in the experiments that we did, we asked people to move back and forth between 2 points as fast as they could, which is not exactly representative of an industrial environment. People don't necessarily move always as fast as they could. But the important point is that at higher frequency, usually the motion are of a smaller amplitude, and we can match that with the system, the MacroMini system that we have. Okay, now we can extend this to try and accommodate the motion of serial robots by mounting some mini robots on the links of the standard serial robot. So in other words, it's like applying the MacroMini approach to robot links. So we cover the links of a robot with some shells that are mounted on passive elastic mechanisms that have encoders in them, so that we measure the motion of the shells and we implement the motion of the robot. We produce the motion of the robot based on these measurements. So this is to provide high reactiveness and intuitivity for low and produce low interaction forces. Now the comparison that we can make of this, it's like if you grab your co-worker's arm and try to help the person, to guide the person to a certain position, you don't directly interact with the bone structure of the person, but you interact with soft tissues and the skin and all that. So that gives you a buffer between, the external shell of the robot and the structure of the robot. So basically the approach is the following. The traditional approach or conventional approach on the left-hand side is we have joint torque measuring devices. The user apply forces to the robot. We measure these interaction forces and react. Whereas what we do on the right-hand side is we have the interaction forces applied to some shells that are mounted on the links, and they are mounted on low impedance mechanisms that are used to infer the intentions of the user. So this is here on the left-hand side a cross-section of the shell with the link. So in the center you can see the robot link. On the outside you can see the shell. And there's let's say here in this case, a planar 3-degree of freedom mechanism connecting the two. And so the implementation that you can see on the right-hand side, where the cover has been removed to show the inside of the link system. So this is the implementation of this 3-degree of freedom mechanism. So as I mentioned before, the joints here are not actuated, the joints of the parallel robot, but they are equipped with encoders. So we can measure this motion and infer the intention of the user. Another thing that I'd like to point out is that the mechanism is statically balanced. Why? because we want to be able to reduce the dead band of the force that we apply to the link. We have elastic return mechanisms to return the shell to its neutral position, but this elastic return mechanism has to be able to return the shell to its reference configuration, whatever the orientation of the link. In other words, whatever the orientation of gravity. And so to make this return action as light as possible, we balance the mechanism. So this is the implementation that we've done. We've built this 5 degree of freedom serial robot. It's basically a conventional robot with actuators, with gear reduction and so on. But on the two links, the proximal shell and the distal shell, we've mounted these shell mechanisms so that we can interact with the robot, and we hope to be able to increase the bandwidth. So this is what you see in this video, and you will see that the bandwidth of the interaction is very high compared to a commercially available robot. You can see here that you can move the robot with very small interaction forces, and you can move the robot swiftly, much more than with conventional approaches of collaborative robots that are available commercially. So here you have two shells mounted on two of the links, and by applying forces on the shells, you can see that you can move the robot either very precisely or swiftly, and you can see the action of the buffer between the motion of the user and the motion of the robot, based on the mechanism that are in the robot shell. Here you can apply forces on both shells at the same time, no problem. You can guide the motion of the robot and fully control, the action of the robot. When we started this project, we started with 6 degree of freedom shells on the links instead of 3, but we found that it was less intuitive to manipulate the 6 degree of freedom shells because it was more difficult to discriminate between the intentions of the user of rotating or displacing the links of the robot. So 3 degree of freedom shells on several links seem to be a good compromise. Now here are some results that we obtained with this. So the top graphs are for our shell system, and the bottom graph is similar trajectory or almost identical trajectories performed with a KUKA lightweight robot. So the interesting curves, again, you can see the velocity curves are almost the same. So we perform more or less the same motion, but the interesting curves are the force. So on the top graph, you can see the solid line that represents the force, which is, let's say, maximum 5 newtons, something like that. On the bottom graph with the KUKA robot, we go to at least 50 Newton of force. So the feeling is completely different. Unfortunately, I'm showing you videos. I cannot make you try the robot, but for such applications, trying the robot, you can really tell, the difference. Okay, now coming back to parallel robots, let's say in their more traditional sense, how could we use kinematically redundant parallel robots for a physical human-robot interaction? And why would it be interesting? Why kinematic redundancy? Well, for several reasons. First of all, to alleviate singularities and obtain large workspaces, because one of the limitations of parallel robots, especially 6 degree of freedom parallel robots, is the limited orientational workspace. So we want to alleviate that. Also, if we use kinematic redundancy, it gives us more freedom to change the form factor of the robot. And also what we want to do is to preserve the fundamental characteristics of parallel mechanisms, that is the force transmission in the mechanism. So by doing so, we want to extend the realm of applications of parallel robots, including physical human-robot interaction. So, for example, let's revisit the Goff-Stewart platform. So this is a very well-known parallel mechanism. Now we want to introduce kinematic redundancy while preserving the force transmission characteristics. Like I said, the characteristic of this robot is that the legs are loaded only in tension and compression. So we introduce parallel redundant legs and so we can avoid singularities and extend the workspace. So this is the way we do it. We start from the standard Gov-Stewart platform. We replace some of the legs by what you can see here on the right-hand side, two actuators coupled together by a revolute joint, and then an extension, which is the redundant link, connected to the platform by a spherical joint. So by controlling the motion of the two sub-legs here, we can control the direction of the extra link, the redundant link, and then control the direction of the force applied to the platform. And this is how we can alleviate the singularities. We've been able to show theoretically that if we replace three of the legs by double legs like this one, in theory, we can alleviate all singularities. So in other words, for any position and orientation of the platform, there always exists a non-singular configuration of the robot. So this is a theoretical proof. Let's look at in more details at the formulation. So first we consider the non-redundant legs of the HPS type. And this is well known, we write the constraint equation of the length of the legs, and we can see that the six component vector that will appear in the Jacobian matrix, the corresponding line of the Jacobian matrix, is simply the Plücker coordinates of the line associated with the leg, the non-redundant leg. If we do the same analysis with the redundant legs, we can see that what we will obtain is the Plücker coordinates of the line that connects the revolute joint at point SI here to the platform. So this is the line appearing in the Jacobian matrix, and because we can change the direction of that line by controlling the two redundant actuators, it means that we can rearrange the vectors of the Plücker vectors connecting to the platform and avoid the singular configurations. Now, I want to stress the fact that this arrangement is kinematically redundant. It's not redundant. It's not actuation redundancy. It's kinematic redundancy. So the robot, if we replace three of the legs by double legs, the robot has 9 degrees of freedom and 9 actuators. So there's no force constraint introduced in the robot. So the Jacobian matrices, like I said, look like this. Some of the lines correspond to the Plücker lines of the redundant links, and the standard legs, they have the Plücker lines of the legs themselves. This allows us to extend the workspace, especially the rotational workspace, considerably. This plot here is a plot of the workspace in the tilt and torsion space. Unfortunately, I didn't include a comparison with the workspace of the standard Gov-Stewart platform, but this workspace here is much bigger than what you find for a standard Gov-Stewart platform because of the singularities that quickly appear in the Gov-Stewart platform. In a standard Gov-Stewart platform, you can tilt the platform to an angle of, let's say, about maximum 45 degrees if you're lucky, but not beyond that because you start running into singularities. Here with this robot, and you will see in the video here, this is a 6 plus 3 degree of freedom robot. We've modified 3 of the legs to make double legs. And here you can see the orientation capabilities. So we can tilt the platform to 70 degrees all around, and in some directions even more, like 80 and sometimes 90 degrees. So the limitations are due to mechanical interferences, but no longer to singularities, because we can alleviate that. Same for the twist motion. For the Gov-Stewart platform, it's well known that you cannot exceed 90 degrees. Here we can exceed 170 degrees. This is an illustration of the redundancy. You can see the motion of the redundant legs, and the platform is not moving. We also had to develop our own spherical joints because the rotations are large, and so standard spherical joints could not accommodate that. So now, I think the lesson to learn from this is that by introducing kinematic redundancy, we can increase the rotational workspace of parallel robots and make them suitable for physical human-robot interaction. Because if you use the standard Gov-Stewart platform, it's not that appropriate for interaction because people interacting with the robot will expect more range of rotational motion. So based on that, we went back to the drawing board and said, okay, now we're able to do redundant hybrid and parallel robots. How would we build a robot for a physical human-robot interaction based on this concept? So we want to, of course, have low moving inertia, which is the case with parallel robots. We want to have backdrivable actuators at the base or near the base. So perhaps using linear actuators like in the robot that I've just shown, perhaps that's not the best solution for us. Maybe we would prefer to have Revolut actuators. Also, having 9 legs, like in the robot that I've just shown, may not be the best solution either, because there's quite a bit of cluttering, and maybe we should reduce the number of legs and make it a hybrid robot where some of the legs, or the different legs, would have more degrees of freedom and maybe not completely parallel. We want to make sure we have a large range of rotational workspace, more than 90 degrees in tilt and in torsion. And also, perhaps we could exploit the redundancy to do something else than just avoid singularities, but, for example, to operate a gripper. Because, avoiding certain configurations means that there are still infinitely many other configurations that you can use. So maybe you can use this motion to do something else. And so we also target a MacroMini robotic system. So we want to build a parallel robot that would be more or less like a small robot that would be mounted on a big, let's say, for example, the gantry robot that I've shown before. So based on these criteria, we selected an architecture with 3 legs and 3 actuators per leg. That's 9 degrees of freedom, similar to what I've just shown, but with a different architecture and less cluttering. We also designed an architecture with Revolut joints instead of prismatic joints. So we came up with this architecture that you can see here. On the left-hand side, you see a picture of the prototype that we built. It has 3 legs. In each of the legs, there are 3 actuators. 1 is fixed, and the other 2 are just moving around the axis of the first one. They're just sort of like pivoting, and they drive a parallelogram 2-degree of freedom mechanism, which provides 3 degrees of freedom for each of the legs. And then we have the redundant links that connect the legs to the platform. And the way we intend to use this robot is pictured on the right-hand side, where we have this parallel robot mounted on a gantry robot, and the user is interacting with the small parallel robot, and the gantry robot provides the large workspace to bring the mini robot to different configurations. So this is another illustration of it. So in each of the legs, you can see the base Revolut joint, which is actuated, and then the 2 joints, the 2 actuated joints at the base of the parallelogram up here. And so this 3-degree of freedom leg allows you to position the spherical joint here at point SI. And then you have the redundant link connected to the platform by this Revolut joint. You have 3 such Revolut joints on the platform. So by doing the kinematics of this, we can see that the direction of the redundant links can be controlled independently from the position and orientation of the platform. Now, if you do the singularity analysis, you can see that the constraint wrenches applied to the platform are a force along the redundant link, and also a force going through the spherical joint in a direction parallel to the Revolut joint at the platform. So you have 6 such constraint wrenches, and so you can analyze the singularities of the mechanism based on that. So by considering these wrenches, we can write easily the Jacobian matrices, which again are constituted with the Plicker coordinates of these lines. And then by rearranging the Jacobian matrix, we can see that writing these quantities in the frame of the platform, we obtain the matrices Jn and Ja that are shown here, and we can see that they're completely decoupled. And so analyzing the singularities is easy because all we have to do is to analyze the singularities of the two block matrices separately. And so it's quite easy to show that we can alleviate singularities of the JN block simply by choosing the length of the redundant link, making them short enough. And the singularities of the second block can be avoided by choosing the range of motion of the redundant link within a certain range. So this is what you can see on the right-hand side. You can see the end effector platform, and the dotted lines define the range of motion for each of the legs. If you stay within that range, there will never be a singularity of the second block. So this is, knowledge that we have from planar parallel robots. It's very simple to show that. So this is interesting because it means that by design, we can make sure that there will never be type 2 singularities for this parallel robot. So if we have mechanical limits on the motion of the redundant links with respect to the platform, we can guarantee that there will never be singularities. Okay, so the picture is a little bit complicated here, but essentially what we do here is we replace the revolute joints at the platform by parallelograms, and we use this motion to operate the motion of the jaws of a gripper so that the redundancy can be used to operate the gripper. It means that we can control the gripper from the base actuators, and so we don't need to have any actuator or in fact any cabling that goes to the end effector. We also statically balance the legs, and this is so that we can limit the actuator forces that are due to the weight of the platform. And here I'll show you a video of the prototype. So here you can see the actuators at the base of each leg. You can see the end effector. And if you compare the footprint of the robot with the workspace, you can see that for a parallel robot, this is a fairly large workspace. You extend beyond the footprint, and also for rotational, you can see that the rotational workspace is very large. We can tilt to 90 degrees in each of the directions, no problem. And the twist motion also can be fairly large. The robot is also, here you can see a rotation, through the different tilting directions. Remember, the robot is intended to be mounted upside down. This is operating the motion of the jaws, and these are the dynamic capabilities of the robot. And yet, if you move at these velocities and accelerations, the robot remains safe because the moving inertia is small. Now, in terms of interaction, the robot is completely back drivable because there are no gear reductions at the base. So here you can see the person moving the robot very easily, very freely, deploying their own impedance. And this is because, the robot is lightweight, direct drive, back drivable. So there is no need for a force torque sensor to be able to interact with the robot. Here the person is just guiding the robot to teach different positions, poses of the end effector. And so that makes it very easy. Again, you can keep in mind that, the robot would be mounted on a gantry robot, for example, for the person to interact with. Here's a demonstration of the fact that we could use the robot as a haptic interface also, or we could make the user feel some things. For example, if we don't want the robot to move in certain areas of the workspace, we can have a virtual wall, and the person will feel the contacts with this virtual wall and say, okay, robot is preventing me from going to this area for some reason connected to the application. So here, the same. Now we cannot move in the other direction. We have this virtual wall that's present, and that's something that we can do quite well. In fact, due to the fact that the robot is back drivable and we have no gear reduction. Then you will see the robot performing a certain task, or the person teaching the robot a pick and place task. What's interesting here is because the actuators of the robot also drive the opening of the gripper, the user can teach also not only the position, but also the opening of the gripper, and so teach the robot different points of the trajectory. This is now the intermediate point, and then the robot just repeats the trajectory. So goes to the pickup location, closes the jaw, grasps the object, bring it to the intermediate position, and then to the final configuration. So again, keep in mind that the robot is upside down, and so that's why we had to build these little shelves here, but in principle it would be much easier than that. Then the robot repeats with a different object, but it's essentially the same. So here the robot is moving fairly slowly, just because the student was careful with the experiment, but in fact the robot is capable of moving much faster, as you saw before. Okay. By the way, these videos are available on our lab's YouTube channel. So if you go to YouTube and type the Laval University Robotics Laboratory, you will find all these videos and 100 others. Okay, this is how we intend to use the robot. And this is currently the situation where we have the robot mounted on the gantry, and we've started to do some experiments where we can move the robot to different locations. And that way we can have a very large workspace and at the same time have a very swift interaction and intuitive interaction with the robot, with the person using the robot. Okay, so in conclusion, we think that parallel robots have great potential for physical human-robot interactions, and the reasons being that they have low moving inertia and they can be built to be backdrivable, which removes the need for force torque sensors and makes the control much easier and more intuitive for the user. In order to be able to do that, we've used kinematic redundancy. I think that's an important thing in our work, because it allows us to extend the workspace of parallel robots and alleviate singularities. And so we were able to greatly increase, in particular, the rotational workspace, which is the most important part. We were also able to leverage the kinematic redundancy to operate a gripper, which is a very interesting feature of the robot. Maybe I want to just mention, I mentioned the rotational workspace more specifically. The reason is, if you want to extend the translational workspace of a parallel robot, you can always build a bigger robot and you will increase the translational workspace. But the rotational workspace is more difficult. If you build a bigger robot, there is no impact on the rotational workspace because of the possible singularities. Okay, so finally, we think that we can extend the realm of applications of parallel robots through the development of novel architectures like the ones that you've seen today. In terms of future work, we want to work on the optimal design of the robot architectures, number of redundant legs, geometry, and so on. There are still open possibilities. Integration in the MacroMini robotic systems. I've shown you what we're doing now, so this is the next step. And the synthesis of other kinematically redundant parallel mechanisms. I want to acknowledge the funding of NSERC, the Natural Sciences and Engineering Research Council of Canada, the Canada Research Chair Program. And the names that you see at the bottom here are students and research associates who've been working on the robots that you've seen today. So they are the ones doing the actual work of implementing all these theories and these controllers and developing the design of the robots. So I want to acknowledge them sincerely for all the work that they've done. Okay, so I will stop here, and I thank you for your attention. Again, if there is time, if there is a means of doing that, I would be happy to entertain any questions that you would have. Thank you.
Thank you very much, dear Clement, for very nice speech. I see a chat box, many questions received about your speech. Okay. One of the question is, I read it. Oh, Dr. Tagarov say,
Maybe Arya, I can ask in person if you don't mind.
okay.
It
Very
will be
good.
faster that way. Thank you, Clement. It was really, really interesting for me, since it is, somehow we are working on similar areas. I have three quick questions. First, you talk about, impedance, low impedance structures several times in several applications. Are these impedance, low impedance, are made by mechanical structure only, or you are also having impedance controller or adjustable impedance controller on them?
Both of them, but mainly we start with a low mechanical impedance from the mechanical structure of the robot, so that it's much easier then for the controller to make sure that we render a low impedance to the user.
Okay, and my second question is exactly on that. If this is the case, and you have also low impedance controller structure on them, did you find any application or any real time application that you need this impedance to be somehow variable or adaptive, and doing it through the controller? And if this is the case, I would be more than happy to hear which applications.
Yes, a good application, a good example of that is the haptic interfaces. When I showed the virtual walls, we would like the impedance to be, to the contact with the wall to be sharp. So the person really feels that, there is something there that you shouldn't go in that direction. And so that needs, that requires us to adjust the impedance of the interaction. So in the controller, we do that so that we can make the user feel that these contacts as sharply as possible. So that's an example application.
Oh, perfect. And my final question is, I saw so many large gantries in your lab. Although you are one of the pioneers of cable robotics for large workspace application, why you are not using cable robotics for the general structures?
That's a great question. It would be very nice to use the cable robots for that, but for this specific project, we target industrial applications, and we also work with industrial collaborators, and they are used to using gantry robots. It's very common in industry. That's one reason. Another reason is because in this project, we want to demonstrate the interaction with the robot, the mini robot, and so it's simpler for us to use a gantry robot because, as you know, the cable robots. We have some cable robots, but it's experimental. It's prototypes. It's a little bit less easy to use in the lab. We want to focus on the mini robot. That's another reason. It's a very practical reason. Yeah.
Okay.
But the cable robot is a great idea, of course.
Okay. Thank you very much. Thank you very much.
Thank you, Dr. Other question is, what the programming language of choice that your team prefer to use? Do you use Python, or due to the latency, do you prefer some alternatives?
Okay, the controllers that we use in the examples that I've shown are based on a real-time software called the RT Lab. And so what RT Lab does is the way it works is we write the controller, we develop the controller using Simulink, and then there is an automatic program that transforms the Simulink programs into C programs automatically, and then we compile the C programs on a real-time kernel. So the real-time program that we obtain at the end is very responsive and very stable. So we don't use Python, and we use a real-time controller based on the program RT Lab.
No, thank you. Other question is, what controller type are used for motion control of hybrid parallel robots, maybe model-based controllers?
Yes, yes. So we have a dynamic model of the robot that we implement in the controller. So when we move fast, for example, we know we can compute, we use the computed torque approach. We can compute the torques that are required. And so we use that as a feed forward in the controller. And so it's a very standard controller based on a model of the robot.
No, thank you. Another question, I think last question. Dr. Mehdi Talemasoule say, my dear great professor, just to say hello and have the permission to have some words. Dr. Masoule says.
Hello, Mehdi. Nice to hear from you.
Is there any time delay between human influence and a robot motion? If yes, how you deal with it?
Yeah, that's a very good question. And that's one of the reasons why we want to use impedance control instead of admittance control, because the reaction is more direct. So the person is moving the robot, and the robot is sensing this motion through its encoders. So this is more direct than having a force torque sensor and having to translate this into the intention of the user and then drive the control of the robot. So by using impedance control instead of admittance control, by having the robot back drivable, we considerably reduce the delay between the action of the person. It's a direct mechanical action of the person instead of going through a controller. So it makes a big difference in terms of the interaction. When you interact with the robot, it's very, very smooth.
Thank you very much.
I have some just very small question regarding maybe it's following the last question of Dr. Taghirat. If there is a possibility, because actually one of my PhD students is working on blending and merging cable robots and solid parallel robots. And the question is that if there is some possibility to merge this robot in order to have collaborative robots, and the question is going more about the finger robotic hands. What we are actually doing in my laboratory is to, in fact, merging cable robots with solid robots in order to build some new robots. Do you think that we are able to do this concept and to use this concept in using finger robots?
Yes, like I said to Professor Taghirat, I think it's a great idea to combine cable robots with parallel robots. The issues there would be, I think, the dynamic interaction between the two, because if you have the parallel robot producing some reaction forces on its base, you have to make sure that the cable robot will be able to withstand these reactions and not introduce some excitation of the parallel of the cable robot due to that. But I'm sure it's possible to do it. You just have to be careful in terms of the dynamic interaction and do some dynamic analysis to make sure that this will be handled correctly.
Thank you very much. And the last thing that I have to say, je me souviens, comme en fait, in the every cards that we have in Quebec City, that in the Quebec, in fact, and I remember, in fact, every great moments in Quebec. Thank you very much, Doctor.
Thank you, Mehdi.
Thank you so much. I think this time is over. Thank you, dear Professor Clement Gosselin, for your nice speech and valuable attendance during this conference. Thank you so much.
Thank you everybody. Thank you for your attention, and have a great evening.
Thank you. Bye-bye.
Thank you, Clement. I hope to have you sometimes in Tehran, hopefully after pandemic, just right after pandemic. I will take this opportunity to invite you on beforehand, and I hope that you can find some time from your very, very busy schedule to spend with us and your former graduate students who are in Iran working on parallel robotics. Thank you for accepting our invitation, and have a great day.
Thank you. Thank you very much. And I really appreciated having this opportunity to talk with you today and hopefully maybe someday in person. Thank you.
Thank you so much. Bye-bye.
Bye-bye.
Thank you. Bye-bye. Thank you very much.
خب خیلی سپاسگزارم از توجه دوستان. امیدوارم که روز خیلی خوبی رو تا اینجا سپری کرده باشید. ما میخوایم بریم سراغ بعد از یک بریک کوتاه دیدن یک بخشی از یک کلیپ جذاب، میخوایم بلافاصله بریم سراغ سخنران کلیدی بعدیمون که یکی از عزیزان و بزرگانی هستن که تلاش‌های بسیار زیادی در گسترش دانش در کشور عزیزمون انجام بدن. با ما همراه باشید. رأس ساعت 6:15 انشالله اینجا سخنرانی کلیدی بعدی رو با هم دیگه آغاز می‌کنیم. سپاسگزارم از توجه شما.